The universe is teeming with planets. I want us, in the next decade, to build a space telescope that'll be able to image an Earth about another star and figure out whether it can harbor life. My colleagues at the NASA Jet Propulsion Laboratory at Princeton and I are working on technology that will be able to do just that in the coming years. Astronomers now believe that every star in the galaxy has a planet, and they speculate that up to 1/5 of them have an Earth-like planet that might be able to harbor life. But we haven't seen any of them. We've only detected them indirectly. This is NASA's famous picture of the pale blue dot. It was taken by the Voyager spacecraft in 1990 when they turned it around as it was exiting the solar system to take a picture of the Earth from 6 billion kilometers away. I want to take that of an Earth-like planet about another star. Why haven't we done that? Why is that hard? Well, to see, let's imagine we take the Hubble Space Telescope and we turn it around and we move it out to the orbit of Mars. We'll see something like that, a slightly blurry picture of the Earth because we're a fairly small telescope out at the orbit of Mars. Now let's move 10 times further away. Here we are at the orbit of Uranus. It's gotten smaller, it's gotten less detail, less resolve. We can still see the little moon. But let's go 10 times further away again. Here we are at the edge of the solar system, out at the Kuiper Belt. Now it's not resolved at all. It's that pale blue dot of Carl Sagan's. But let's move yet again 10 times further away. Here we are out at the Oort cloud, outside the solar system, and we're starting to see the sun move into the field of view and get into where the planet is. One more time, 10 times further away. Now we're at Alpha Centauri, our nearest neighbor star, and the planet is gone. All we're seeing is that big beaming image of the star that's 10 billion times brighter than the planet, which should be in that little red circle. That's what we want to see. That's why it's hard. The light from the star is diffracting. It's scattering inside the telescope, creating that very bright image that washes out the planet. So to see the planet, we have to do something about all of that light. We have to get rid of it. I have a lot of colleagues working on really amazing technologies to do that, but I want to tell you about one today that I think is the coolest and probably the most likely to get us an Earth in the next decade. It was first suggested by Lyman Spitzer, the father of the space telescope, in 1962, and he took his inspiration from an eclipse. You've all seen that. That's a solar eclipse. The moon has moved in front of the sun. It blocks out most of the light, so we can see that dim corona around it. It'd be the same thing if I put my thumb up and block that spotlight that's getting right in my eye. I can see you in the back row. Well, what's going on? Well, the moon is casting a shadow down on the Earth. We put a telescope or a camera in that shadow, we look back at the sun, and most of the light's been removed, and we can see that dim, fine structure in the corona. Spitzer's suggestion was we do this in space. We build a big screen, we fly it in space, we put it up in front of the star, we block out most of the light, we fly a space telescope in that shadow that's created, and boom, we get to see planets. Well, that would look something like this. So there's that big screen, and there's no planets, because unfortunately it doesn't actually work very well, because the light waves of the light and waves diffracts around that screen the same way it did in the telescope. It's like water bending around a rock in a stream. And all that light just destroys the shadow. It's a terrible shadow. And we can't see planets. But Spitzer actually knew the answer. If we can feather the edges, soften those edges, so we can control diffraction, well, then we can see a planet. And in the last 10 years or so, we've come up with optimal solutions for doing that. It looks something like that. We call that our flower petal star shade. If we make the edges of those petals exactly right, if we control their shape, we can control diffraction, and now we have a great shadow. It's about 10 billion times dimmer than it was before, and we can see the planets beam out just like that. That, of course, has to be bigger than my thumb. That star shade is about the size of half a football field, and it has to fly 50,000 kilometers away from the telescope that has to be held right in its shadow, and then we can see those planets. This sounds formidable, but brilliant engineers, colleagues of mine at JPL, came up with a fabulous design for how to do that, and it looks like this. Starts wrapped around a hub, separates from the telescope, the petals unfurl, they open up, the telescope turns around, then you'll see it flip and fly out that 50,000 kilometers away from the telescope. It's going to move in front of the star, just like that, creates a wonderful shadow, boom, we get planets orbiting about it. Thank you. That's not science fiction. We've been working on this for the last 5 or 6 years. Last summer, we did a really cool test out in California at Northrop Grumman. So those are 4 petals. This is a subscale star shade. It's about half the size of the one you just saw. You'll see the petals unfurl. Those 4 petals were built by 4 undergraduates doing a summer internship at JPL. Now you're seeing it deploy. Those petals have to rotate into place. The base of those petals has to go to the same place every time to within 1/10 of a millimeter. We ran this test 16 times, and 16 times it went into the exact same place to 1/10 of a millimeter. This has to be done very precisely. But if we can do this, if we can build this technology, if we can get it into space, you might see something like this. That's a picture of one of our nearest neighbor stars taken with the Hubble Space Telescope. If we can take a similar space telescope, slightly larger, put it out there, fly in a coulter in front of it, what we might see is something like that. That's a family portrait of our solar system, but not ours. We're hoping it'll be someone else's solar system, as seen through an occulter, through a star shade like that. You can see Jupiter, you can see Saturn, Uranus, Neptune, and right there in the center, next to the residual light, is that pale blue dot. That's Earth. We want to see that, see if there's water, oxygen, ozone, the things that might tell us that it could harbor life. I think this is the coolest possible science. That's why I got into doing this, because I think that will change the world. That will change everything when we see that. Thank you.